Hey everybody, Mr. Judson here. So I told you we were going to have to kind of go back and revisit our trig functions and change things slightly, a little bit, because of the chain rule, all right? So we're going to rewrite all of our definitions of our derivatives for trig functions, and I would say once we've done this, now we're to a point where you can start making your note cards, all right? So what I'm going to do is I'm going to say that the derivative of a sine of u, so before we just had sine of x, right? Well, now we're saying we can have any angle. It doesn't have to be just x. It could be x squared. It could be the sine of 2x squared minus 5x. It could be the sine of a cosine of x. It can get messy, all right? And this equals the cosine of u. That part hasn't changed, but with the chain rule, we always had to go back and take the derivative of what's inside. Now we've got to take the derivative of that angle. Okay, so the cosine, whatever this angle is, it stays the same, but then times the derivative of the angle. So if I took the derivative of a cosine of u, we know that's going to be a negative sine of u times u prime. I would almost rather write the u prime in front, so I know that this is not part of the angle. Here's my angle, but we're multiplying it by something in addition, okay? If I'm taking the derivative of a tangent of u, that's going to equal a secant squared of u, there's my angle, times the derivative of what's inside the parentheses, u prime. So my derivative of a cotangent of u is equal to a negative cosecant squared of u times u prime. If you think about this, if this was sine of x, this would be the cosine of x times the derivative of x, which is 1, and that's why we didn't have to worry about this before. We were just multiplying by 1. Now we got to start worrying about it. If I had the derivative of a secant of u, that would equal a secant u times tangent u, here's my two angles, times the derivative of what's on the inside. And the derivative of a cosecant of u is going to equal negative cosecant u cotangent u times u prime. So really the only difference here is all of these are saying whatever the angle is, you got to multiply by the derivative of that to really do it correctly. Okay? All right, let's try a couple examples. All right, so we want to find the derivative of this. And so I would say y prime equals, the derivative of a cosine is a negative sine of the same angle, pi x minus 3, times the derivative of that angle, which really that's just pi. And if I was going to write this again, I'd want to put that pi out in front just so that I don't think it's part of the angle. All right, let's try another one. This time I've got f of x equals x squared minus 1 times the sine of x squared. You guys see if you can find that derivative. So when I look at this, what I see is a product rule. And so when I do the derivative, I've got to do the derivative of the first times the second piece plus, leave this the way it is, times the derivative of that, which would be a cosine of x squared, times the derivative of the angle, which would be 2x. And so I probably should at least distribute this times each of those. So that means my answer is going to be 2x sine of x squared. You can put that in parentheses if you want, but you don't have to. I'm going to take 2x times x squared and get 2x cubed times a cosine of x squared. And then that times 1, so I'll get a negative 2x cosine of x squared. And they aren't like terms. You know, my trig function's the same, but not my variables. So I can't add those. This trig function's different. And so that's it. That's as far as I have to go. Let's try this one. This time I've got f of x equals the square root of the tangent of 2x. You guys go ahead and try it. All right, so I think what I want to do with this first is I want to write this as tangent of 2x raised to the 1/2 power. And so what I see is something inside parentheses raised to an exponent, which means chain rule. So when I take the derivative of this, I need to bring the exponent down in front, subtract 1 from that, everything inside stays the way it is, times the derivative of the inside. So the derivative of a tangent is a secant squared, times the derivative of the angle. So let's see, that means 1/2 times 2 is going to be 1. So I can ignore that. This derivative is going to be a secant squared of 2x over, when I drop this down below the fraction bar, it becomes the square root of a tangent of 2x. And because of the square root, we really can't do anything else to simplify this. I can't use my properties and, you know, our trig simplification stuff that we did last year. I can't do that on this problem. I'm just kind of stuck right there. There's my answer. All right, we've got this y equals the sine squared of 4x minus 2. Something we really got to be careful of here is when we're squaring a trig function, what that really means is I've got a sine of some angle, 4x minus 2, and I'm squaring that whole thing. Okay? I need to always take trig functions raised to an exponent and write it this way, because then when I look at that, that means I've got something inside parentheses raised to an exponent. That's a chain rule. Along with a trig function's got a messy angle. To me, a messy angle is anything other than x or theta. All right? You guys go ahead and try that. See if you can find that derivative. All right, so y prime, I need to bring my 2 down in front. Subtract 1 from the exponent, times the derivative of the inside, which is going to be a cosine of 4x minus 2, times the derivative of the angle, which would be 4. So overall I've got 8, when I multiply these two, sine of 4x minus 2 cosine of 4x minus 2. Oh, I don't know if we're going to see this as an answer. So we had something last year called the double angle formula. You guys remember that? The sine of 2 theta was equal to 2 sine theta cosine theta. And whenever I see a sine of an angle and a cosine of an angle, especially if there's an even number there, that makes me think of this. right? So if I took this and made this 4 times 2, so 2 sine theta cosine theta is really equal to sine of twice that angle. So our book may take this and say the answer is really 4 sine of twice this angle, which would be 8x minus 4. This is where I think COVID kind of hits us, because you guys would look at that and go, oh, okay. If it was a normal spring semester last year, I don't know if we're doing that. I wish I could see you guys right now to see the reaction on your face. If that double angle makes sense to you and you can see that, I think that's great. But you know, if somebody took this right here and just said, I'm good right there, you know, I could see that. But and I'm okay with this. I just think when you see that in the back of the book and you go, whoa, how did that happen? That's why. You know, we want to understand why something happens. All right, that's really it. Today we're also going to get a few problems with the chain rule where they ask us to find the slope of the tangent line. That just means do a chain rule and plug in an x value, see what the slope is. Or find the equation of the tangent line using a chain rule. That's fine. If you give me a point, all I got to do is plug in the x value and I got the slope. I can get the equation of my tangent line. So we'll see a few problems like that as well. All right, that's it. That's what we have for today. Let me get you guys an assignment. All right, so assignment number 10. We're in our 10th week now. Page 140, we're going to do 37 to 46, 49, 65, 66, 70, 71, and 75. All right, that's it. You guys have a good day. Stay safe. Take care of yourselves. We'll see you later.